So, we are going to introduce predicate logic. Predicate logic is also called sometimes it is called quantifier logic. It is also sometimes and the version we are going to study specifically is called first order logic. And the question of what exactly first order means is something that I will talk about later after we have defined the syntax maybe. So, let us start with predicate logic or quantifier logic. So, the important thing to realize is that there is something about okay, or maybe I will come to that as we proceed. Yeah, okay. So, the most famous valid argument since the time of Aristotle, which introduces the subject, I mean might as well do this, is this famous thing that all men are mortal, Socrates is a man, therefore, Socrates is mortal. I mean, so the interesting thing about this argument is that all the sentences are very simple sentences. There are no propositional connectives, and so there is and yet it is sort of a valid argument. And what we would like to know is exactly therefore, what is and it is not provable in propositional logic, since all of them are simple sentences. You will give all of them separate propositional symbols. I mean, they cannot be broken up and I mean, they are not compound propositions, they are all simple propositions. And so, essentially you will never be able to prove the validity of this argument from propositional logic, right. So, so there are other similar things, but what we should do is it is instructive to just look at this argument and see therefore, what is actually lacking in propositional logic. Yeah. Okay. One thing of course, is that the propositional connectives are more or less like except for the negation. Yeah. The propositional connectives are more or less actually like prepositions in the language, right, or conjunctions in the language. So, they are basically they connect different sentences, different simpler sentences maybe, and whereas here we are looking at something that goes somewhat deeper into it, and that is that. So, there are no propositional connectives visible any way that you might transform these sentences. So, there is something else happening which we should look at, and that is that. So, firstly what happens is that in this kind of an argument there is an, even though all the sentences are simple, there is a certain internal structure which is somehow being used. But remember that at a fundamental level we still want logic to be syntactic and based on forms, right. But the point is that the propositional forms have been exhausted, and then if you have to actually have an expressive logic which can account for a large amount of the kinds of reasoning we do, then we require to have a better idea of the internal structure of these, even these simple sentences. So, in particular what happens is that there are certain keywords like all and some, and there are certain properties which are essentially like, they are in a linguistic sense they are like adjectives. Okay, so, they are not prepositions or conjunctions. So, there are properties of certain objects like mortal for example, and then there is a description of essentially classes of objects. So, that is which is not there in in the propositional case. So, which means that and then when you are talking about classes, you are essentially talking about membership in classes, and you are talking about sometimes relationships between different classes. Okay. So, if you look at so predicate logic essentially means that there is something in the internal structure which somehow has to bring into take into account classes, relationships between classes of objects, and not I mean, so any argument that goes beyond singular objects or individual objects requires a different kind of treatment. So, linguistically there is this question of looking at adjectives which are like properties, relationships, classes of objects, the relationship of individuals to classes, essentially membership in classes, and these kinds of things somehow come out from the internal structure of these sentences. Until you have actually formalized them, it is unlikely that you are ever going to be able to prove that such a simple argument which is sort of obviously valid should also be valid. So, there are other kinds of arguments like which we should be able to deal with. So, like all men all cats are mammals, all mammals have vertebra, therefore, all cats have vertebra. So, those are like what are known as categorical propositions. The keyword in all the sentences is all, and it is categorical in that sense. Supposing you had all cats are mammals, some mammals do not have vertebrae, some cats do not have vertebrae. So, therefore, some mammals do not have vertebrae, for example. So, there are some specializations of all and some, and which make these categorical propositions. So, you need to look deeper into their structure. Yeah. So, and mathematically speaking, of course, actually it is the most obvious thing to do is to actually parameterize propositions. So, we sort of parameterize the propositions. So, what we will have are parameterized propositions, and these parameterized propositions are called predicates, yeah, from which the logic gets its name. Yeah. So, a proposition by whatever we have so far seen is a declarative statement for which at least theoretically there exists a truth or falsehood assignment. A parameterized proposition is one whose truth or falsehood cannot be established from the proposition itself, but only when the parameters are replaced by singular individuals can you actually establish a truth or falsehood for the proposition, right. So, you take say a property like so from elementary number theory, you take a property like being a number being a prime, right. So, prime x is a parameterized proposition. Prime x by itself, where x is just a parameter, a sort of a placeholder, is not capable of being assigned a truth value, true or false. It can be assigned a truth value only if you replace that x by some individual number like prime 2. Okay. So, that could be true or false. So, prime 2 becomes a proposition, prime x is a predicate in the sense that it is just a parameterized proposition, and the parameters are just placeholders for replacing individuals, for replacing the placeholders by individuals, right, in which individuals can be substituted. And so, a predicate does not become a proposition till all the placeholders get plugged in, yeah, and there can be more than one placeholder. So, usually these predicates therefore, and by using predicates, by using parameters, essentially what what you manage to do is that you manage to also specify. So you can think of these so parameterized propositions, you can also think of them as like going from propositions which are like constants to propositional functions which are propositions of some variables, right. So predicates can also be thought of as propositional functions. So where the placeholders, there might be many different placeholders and they establish a certain structure, and truth or falsehood cannot be determined till values are actually substituted in the places, in the various places. Yeah. So the other way to look at things is that the propositions of propositional logic are zero-ary predicates, and important thing here now is that we have this. So essentially our primary purpose besides a linguistic, besides a purely linguistic foray into logic, is also to is that of describing mathematical theories, right. So when you look at any mathematical theory, group theory for example, then what you have, there is a high prevalence of functions and relations and expressions involving functions and relations. Yeah. So which means that they are about, very often they are about, these functions and relations often are used to describe infinitary objects or infinite classes in some finitary representation, right. So bringing down the infinite to some finite expressibility is a proper exercise in mathematics, right, and that is something that we have to take into account. And by and large, okay, so by and large, whatever reasoning we do in this first order logic is more or less applicable to most mathematical theories. There is a subtle instance, there is a subtlety about the logic being first order and what that actually means. So what we will do is, let us think of propositional logic as essentially being 0th order. So we will say that propositional logic is essentially 0th order. Yeah. When we talk about predicates or first order logic, then what we are talking about is a class of individuals. So usually we are talking about a mathematical theory which has some universal set, okay, and this universal set is non-empty, and what we are looking at are properties of let us say elements of this universal set. Okay. It is possible to look at properties of subsets of this universal set. Okay. So what makes a logic first order is the fact that you are not interested in properties of subsets, you are interested only in properties of individuals. So you are looking at fairly general properties about individuals only in that set, and you might be able to characterize various subsets of this universal set by describing properties of individuals in some parameterized fashion. Okay. But properties of classes or which essentially properties of subsets and being able to describe properties of classes of subsets of this universal set is outside the domain of first order logic. That is so at the moment. So, we are only looking at this, we are not so we are looking at essentially propositional functions maybe of the form p of x, but given subsets of u, we are not looking at propositional functions of this. I mean, that is what. So, the moment, so this is outside the domain of first order logic. So, we are only looking at propositional functions expressed in terms of individuals in the set, and given that there is a subset of u which might, for which this property p might be true, we might be able to characterize subsets of u that way, but we will not be able to characterize properties of subsets of subsets, I mean classes of subclasses of this set, right. So, we will not be taking into account this. The moment you allow this also into your logic, then what you are doing is you are getting into second order. So, essentially what then your domain of discourse really is then 2 raised to u, and then you have two categories of individuals, little x's and big x's, okay. And then you can describe properties of these big x's also. So, when you allow the description of that, then also along with the description of properties of propositional functions on individuals, then you get second order. The moment you go into 2 raised to u, you get third order and fourth order and so on and so on. Ideally speaking, the mathematics does use higher order also. I mean, so second order and third order and fourth order. For example, various characteristic properties of topological spaces are expressed essentially, they would essentially not fall in the domain of first order reasoning. If you were to look at even the principle of mathematical induction, it is not really a first order property, for example. It is a higher order property, and so inductive principles in general are actually higher order, but once you have studied first order, at least the logical extensions to higher order are sort of obvious. The same kinds of quantifiers, quantification rules and so on apply, and so therefore you do not, so it is possible to actually look upon first order logic as essentially being sufficient to describe most of mathematics, right. Okay. So, that is what we are going to do. So, yeah.
How is induction higher order? As in strong induction would be intuitively higher order, but how is normal induction also higher order? Because we consider element by element and then.
No. What you are saying is, you are not saying element by element. You are talking about in induction, what you are saying is a property P of elements, and therefore your induction is saying for all properties P of individuals, if let us say P is true of 0 and the fact that P is true of n implies P is true of n plus 1, then P is true for all the naturals, let us say. But your induction principle actually says this is true for all properties P. Right. So, in that sense you are actually quantifying over the set of properties of natural numbers, and you take any property of natural numbers that characterizes as a subset of the naturals. And when you are saying you are making a statement about all properties of naturals, you are saying for all subsets of naturals. And so, your induction principle, the principle of mathematical induction, you are quantifying over all properties of over the individuals. In that sense, it is at least second order. Okay. What one can do of course is one can restrict ourselves to the particular order and say you take the principle of mathematical induction, restrict it to first order. So, that means you are just looking at properties of individuals and you just characterize maybe subsets of naturals that way. Yeah. So, induction otherwise is actually a higher order property, because implicitly induction quantifies over all properties which satisfy this pattern. So, that is another problem in general with mathematics textbooks and mathematics teaching, is that this exact nature of quantification is never made clear. I mean, so for example, if you look at if you look at say the group theoretic axioms, they will just say x, y, z equals x, y, z and so on and so forth, right. But there is actually a quantification for all individuals x, y and z. Okay. Very often mathematicians just do not write this. Okay. Many algebraists will just write this in very much the same way in which we wrote rules of inference. Okay. We are looking at x, y and z as particular places, and you are looking at skeletal structures. You are saying that the skeletal tree on the left side can be transformed to the skeletal tree on the right side for all possible substitutions of. So, you are looking at it as a macro or a skeletal structure, rather a pattern matching structure rather than as a quantified statement. Okay. So, this is one thing. So, that is one thing, and in general what actually happens is that when a statement is valid, then often it is not necessary to quantify it. So, that is one thing, and secondly, for the purposes of validity, what happens is that if this is valid, then it is not necessary to quantify it. In fact, what we can show is that this is valid if and only if the quantified statement is also valid. So, that is, and therefore, mathematicians often take these shortcuts. What happens is it can be confusing for a beginner, but usually it is actually a logically valid approach, right, in a strict logical sense. Okay. So, what we will do, we will start with the syntax of predicate logic. Okay. So, as usual, I have a set V of a countably infinite collection of what are known as variable symbols. So, as I said, we are talking about propositional functions, very much like the way we move from, let us say, constants, and very much like the way we move from arithmetic to algebra. I mean, just look at the transition in your education from arithmetic to algebra. In the case of arithmetic, you had specific constants and you dealt only with specific constants. When you moved to algebra, you actually graduated to using placeholders without actually looking at specific constants. So, the introduction of algebra naturally gave rise to the notion of variables, right. So, when we graduate from propositions to predicates, which are just propositional functions, we are actually graduating from constants to variables. So, you require placeholders, and so we will assume a countably infinite set of variable symbols. Yeah. And we will also assume a countably infinite collection of function symbols, because in any mathematical theory functions play a very important role. I mean, the operations and functions, we will regard them as being the. And then there are in addition to functions, of course, any mathematical theory also has a collection of relations, and so those relations are what are going to be specified by predicates. So, we have a set of an infinite collection of atomic predicate symbols, right. Then of course, we will use these grouping symbols. Is the color distinction clear? Oh, okay, it is much clearer there than it is here. Okay. So, we will use these grouping symbols, and I have a peculiar problem that this scopes of unary operators and bindings is always something confusing. So, I am using this square brackets. Most logic books will not have the square brackets. Yeah. Okay. And of course, all these above sets are pairwise disjoint, they are all separate sets, right. And we will start with an algebraic notion, and the reason is actually historical and philosophical. If you look at I mean historically speaking, if you look at the development of mathematics from India, for example. So, the development of mathematics was essentially algebraic in nature. It started with numbers, the place value system, arithmetic, and then went on to expressing various geometrical aspects, for example, Pythagorean theorem in a purely algebraic as an equational form, as an identity, right, and then trigonometric relations and so on as essentially as in an arithmetical or algebraic form. You can any kind of algebraic form is also it also has a certain syntax, and therefore, you can think of it as a linguistic form, right. So, what actually pervaded most of ancient Indian mathematics is a high proportion of algebraic reasoning. Okay. So, and therefore, linguistic reasoning also. So, if you look at the formalization of Sanskrit by Panini, that is essentially like defining a formal grammar and formation rules very much in an algebraic sense, right. On the other hand, if you look at the developments in Greek mathematics, starting from essentially starting from Egypt and then moving on to Greece and then coming back to Alexandria, I classify all of that as essentially Greek mathematics. The primary problem there was not of numbers and symbols and manipulation. The primary problems there were all of a geometric nature, being able to predict when the Nile is going to flood the plains, being able to predict the course of the Nile river, for example, being able to do triangulation, being able to walk across the desert and get some navigational aid using the stars and so on and so forth, using the sun in some geometrical fashion, the angle of the sun and so on. So, the entire development of mathematics actually was divorced from there were numbers, of course, but it was primarily geometric in nature, angles, lines, straight lines, planes, heights, distances and so on and so forth. And even up to the 11th or 12th century, if you look at the problems of Greek mathematics, including the Diophantine equations and so on, which we see in an algebraic form nowadays, most of their solutions, for example, how do you solve quadratic or cubic equations, most of those were expressed, quadratics were expressed in terms of areas and cubics were expressed in terms of volumes. So, what we would regard as a simple cubic equation to be solved, the Greeks would actually imagine volumes of rectangular cuboids and cubes placed in certain fashion, or removing subcuboids and subcubes from other cuboids and cubes. So, subtraction was essentially removal of volumes and then the resulting volume and so on and so forth. So, even the solution of equations had an absolutely geometric flavor to it. Okay. And it was always they always drew diagrams in some kind of perspective mode or in some kind of isometric mode and actually try to reason using volumes and areas, and even when they have to deal with second degree equations and third degree equations. Yeah. Okay. So, but the whole point was that with Descartes actually the whole of geometry got algebraized. Once you have a coordinate system and the notion of a point as an ordered pair of real numbers and so on and so forth, and then you use the properties of algebraic properties of real numbers, you have algebraized geometry. And therefore, in a certain sense the interactions between algebra and geometry, so if you take the development of differential or integral calculus, that is also an algebraization of geometry, essentially of curves if you like. And so algebraization is part of linguistics, and therefore, if you are looking at a formal language development, we will look at all mathematical theories also in some algebraized form, right. Okay. So, we will look at signatures. So, any mathematical theory we will think of it as containing a signature. So, this signature essentially gives you a finite or infinite collection of function symbols with their arities. So, this essentially is a specification of their arities, and these predicate symbols have their arities specified by. So, S is just a formal symbol for a sort. So, there is a sort. So, what we are looking at are one sorted signatures. If you were to look at a typical programming language can be thought of as a many sorted algebra. So, there are several sorts like booleans, natural, integers, reals, strings and characters maybe, and on these, and then there are operations between these sorts. So, then instead of using a single symbol S, we will use many symbols S1, S2, S3 to specify essentially the signature of an algebraic system. And this notion of a signature is exactly what your modern functional programming languages also adopt. I mean, this is there is a, so they have this notion of a sort. So, for example, ML or Camel or Haskell has this int and bool and char and so on and so forth, and you specify a signature essentially in terms of these functions and predicates, these function symbols and predicate symbols by specifying essentially their arities, right, and the sort of the domain and the codomain in the case of functions. In the case of predicates, of course, the you can they are thought of in programming languages as functions which take you to booleans, right. So, that is in that sense there are only functions there. So, we will look at this. So, we will assume that you have got some signature specified for each function symbol and each predicate symbol, and we will assume that there is no conflict. So, for every function symbol there is a unique string specification in terms of the sort, and we are looking at one sorted signatures, which essentially means in our mathematical description we are looking at this U as a single sort. Okay. The generalization to many sorted signatures is not very hard. Okay. One could do that too, but it just becomes more complicated and tedious. So, but there are no technical problems with the generalization, but there is also another thing, that it is possible to take the many sorts that you might have, put them all together and call them a single universe, and have distinguishing predicates for the membership in the various sorts. So, you can have membership predicates essentially for the to distinguish between elements of various sorts. So, they would, if you had a collection of disjoint sorts, then you use one predicate to essentially specify membership in a sort, right. So, okay, then the net effect is that either case your many sorted algebra becomes tediously complex. Okay. But even many sorted algebras given a finite number of sorts can be described through one sorted algebras by just adding these extra membership predicates in the signature, right. So, for example, the simplest thing is to take integers and booleans, put them together, take a disjoint union of them, and just have one predicate which specifies whether an arbitrary object taken from this thing is either boolean or integer, right, and have these two predicates, integer something and boolean something, and you can actually everything that you can do with many sorted, at least a finite number of sorts, you can do in a one sorted case. So, it is sufficient for us to consider a one sorted case. So, that is important, right. And then of course, we have this notion, we have this we have a term, we essentially define a term algebra. So, given a signature sigma and we will just assume a one sorted signature, we have the set of terms, sigma terms is defined inductively by this grammar, and I will use this violet color essentially to for terms. Yeah. So, if f has a signature sm arrow s, then f can essentially take other terms as parameters, and this is an inductive definition in which I have gone beyond the usual BNF grammar by specifying also other things in shorthand. So, S, T, U are like our typical are typical members of terms. So, I will use these symbols like S, T and U in violet to denote terms. This x equals x belongs to V essentially says that all the variables are terms, and so on. Yeah. So, of course, in the particular case when this m is 0 means that you have a constant, and instead of writing it as f with this purple parenthesis, very often we will simply write it as f. Yeah. So, that is our syntax of terms, and I have given them a separate color because they essentially specify your mathematical theory, except for the relations that are there in the theory, for which you are going to have predicates. Yeah. So, given a language of terms already sigma terms, then you also have a collection of predicate symbols, atomic predicate symbols. I will use P, Q, R, etcetera for essentially for atomic predicate symbols, but now our predicate symbols are essentially propositional functions. So, they have places, empty places to be filled up. So, an atomic proposition itself means that it will have, let us say, n variables x 1 to x n. So, it will have a propositional form in which these placeholders can be replaced by terms T 1 to T n. Yeah. And then we will have all the propositional connectives. After all, we cannot, I mean, you are going to consider compound propositional forms too. So, we will have all the propositional connectives that we had. I am now calling that set omega naught to signify that it is they are all the propositional connectives like not and or and conditional and biconditional. And then in addition we have these two operators called the quantifiers. If you have an infinite collection of variables V, you obviously have an infinite number of operators here, one for each variable. Yeah. This is for all, one for all for each variable and one there exists for each variable, right. So, we have this. So, this is our signature, this is our collection of operators, and we will use phi and psi as usual as typical members of the set of formulas, and the language now I am calling it P 1 of sigma. So, propositional logic I just called it P naught. Now, since it is parameterized O and it is meant to describe some particular sigma algebra, we parameterize it on sigma. So, P 1 is first order language for describing this for describing essentially the properties of a sigma algebra, right. Okay. So, these sigma formulas are defined inductively this way, and here is my peculiarity, that is that I like to specify the scope of variables of a quantified variable, and I like to delimit them by square brackets. Yeah. So, otherwise I personally have had a lot of trouble just remembering precedences of operators and trying to figure out quantified formulae in textbooks. I find it is really painful. So, instead if you have a clear delimitation of scope like we have in programming languages, it greatly simplifies matters. So, for example, now I do not need to talk about the precedence of operators in this case. Yeah. So, and what is the extent of the scope is something that is clearly delimited by the brackets, though that is an extra piece of syntax. Okay. So, right. So, so the operator precedence conventions are as before. For these new operators, there are no particular new precedences, because anyway the square bracket should take care of it. However, what I am also going to do is that I mean I am going to have a shortcut. I mean having too many brackets is also a terrible pain. So, when you have a formula phi preceded by several quantifiers in sequence with no other propositional or other connectives occurring in between. So, if I just have a sequence of quantifiers, then I will just use a single pair of brackets to so instead of here look at this, for all x there exists y for all z phi, which has 3 pairs of square brackets to specify the scope, but it is simpler to just specify it as for all x there exists y with a single pair of brackets around the phi. So, this essentially tells you the scope. I mean it does not, you do not lose any information, and it is simpler to write. So, that is what we will do. So, and of course, as before we are not really interested in, like most logic books, in these strings and distinguishing between these strings. We are interested only in the abstract syntax trees of these formulas. Any formula is gives you an abstract syntax tree. So, here is some, here are some, this was a propositional formula, an abstract syntax tree. And in an abstract syntax tree, even these scoping brackets become redundant. I mean you do not need them, because scope also follows the tree structure, right. So, so it's actually, so we will think of them only as abstract syntax trees, right. Okay. So, here I do not know whether you can see all the operators here. I think it's the lettering is too small, but here is the formula, and this is like for all x p x and there exists x q x or r x. This is the abstract syntax tree for that. The root operator is this or, and then r is our abstract syntax tree of course starts with predicate symbols and then becomes terms. The terms are also I mean they are also abstract syntax trees on the predicate symbols, right. So, for example, I can have, so here there exists q x, and here is an and, here is this and p of x, and this or is, and then there is a universal quantifier for all x here, and this is the abstract syntax tree of this formula. If instead of x I had some complicated term, then that would have come here, for example, and so we have green labeled nodes which gradually go into violet labeled nodes, basically, So, our abstract syntax trees would look something like that. Okay. There is a far more amount of technical stuff related to the syntax that we need to worry about, because now we have got the notion of, now we have got notions like free variables and bound variables, notions like subterms and subformulas. So, we have a hierarchy now, clearly we have a 2-level hierarchy. There is a hierarchy of the language of terms, and above it there is the hierarchy of the language of predicates, and you cannot mix the two. All your abstract syntax trees should at the root look green, They should either be completely purple if they are terms, or they should start from somewhere green and then start becoming purple, and from within that purple they cannot change to green, for example. That is, so you have a hierarchy of, we have a 2 level hierarchy of terms and predicates, right. Naturally it brings in, so there is a notion of subterms for a term, and these are certain measures that will be useful for performing induction, like depth, the size of a term, and so on and so forth, which can be defined by induction on the structure of the terms. And similarly, but the other complication which quantification brings us is the notion of a binding and scope, and the notion of therefore free and bound variables, right. So, we will in any term, of course, there is something, there is another simplification which we have done. Remember that our language of terms did not have a problem of free or bound variables, whereas strictly speaking, if you have even simple things like this, if you have simple things like this, then the notion of free and bound variables actually have to come up, because even in the language of terms, but we are simplifying life. I mean, for example, this is a bound variable, whereas this is free, right. I mean, so however, we are not, our signature we have specified it in such a way that there are no binding operations, and therefore, there is no concept of a bound variable in terms. Okay. So, that is a simplification that we have done. Okay. But so, we will just look at the variables in a term, and that can be defined by induction on the structure of the terms. Yeah. You need the variables in a term in order to be able to define free and bound variables on predicates, right, because your terms form the underlying subtrees of your predicates. Yeah. Okay. So, we will define for any predicate phi, we will define Fv of phi to be the set of all free variables, and of course, given an atomic predicate P of T 1 to T n, where T 1 to T 1 and T 1 to T n are terms, you just take the union of all the variables in that, in each in all the terms, and that is the set of free variables. And we also sometimes require the notion of a sub formula, but the notion of a sub formula is actually quite trivial. The notion of a sub formula is just that of a subtree of the abstract syntax tree. Yeah. Except that in the case you shouldn't look at subtrees of terms as sub formulas. I mean, the sub formula should still have something green at the top. I mean, they cannot just be pure violet. Yeah. Okay. So, and in the case of not a formula of the form not psi, you just have free variables of psi, and the set of sub formulas is just this. For any of the propositional connectives except not, you just take the union of the free variables of the two components. We have, all of them are binary operators, and similarly you also define your sub formulas as unions like this. And for any of the quantifiers, you remove the quantified variable from the set of free variables of the body of the quantified formula. So, this whatever is within the square bracket, within the scoping bracket, is called the body of the quantified formula, and x no longer remains in that, because x is a bound variable. Okay. Right. So, I am sorry, this should have been changed to, I think there is I forgot to put a backslash. So, this is x 1 to x m all in violet color actually. So, sometimes what we will do is we will just we will write a formula in this fashion. So, I should have used green. So, we will write this to indicate that the set of free variables of phi is contained in this set. Yeah, I will just stop with this, is contained in this set. That means, it is not necessary that all of these variables are used, some may be used. So, we will continue this then later, and we will stop here.